Welcome back to 10 Applied Math. Today we are still continuing solving linear systems, but today we're going to introduce a third method called substitution. So just to recap, we have solved linear systems using graphing by graphing each line on a Cartesian plane, a Cartesian grid, and looking to see where the two lines intersect to find the solution. And we realized that it was a very limited option because we're not always restricted to x and y values that are integers. So when you encounter decimals and fractions, it becomes a rather difficult method to use. So we went to an algebraic method called elimination, where we either added or subtracted our equations to eliminate either the x or y value. And so today we are looking at a third method, also an algebraic method, and this method is called substitution. Now we all know the word substitution. We think about a substitute teacher that comes in and replaces your teacher. Now hopefully that person is able to be an exact replacement. Even when you're baking, when you're asked to use milk, maybe you're going to use something equivalent like a rice milk or a soy milk if you have issues with dairy. But the idea is to replace something with equal value. And that's what we're going to do here. And this is a bit tricky. So we have two equations. We have equation A and we have equation B. Now, what we want to do is we want to replace one equation into another. So when you look at that, this 2x plus 2, what is it equivalent to? Well, it's equal to y. And if you look at the second equation, we have x minus 1 is also equal to y. So this here equals y, and this here is equal to y. So if they're both equal to y, are we then not allowed to say 2x plus 2 must equal x minus 1? Because this is y and this is y. And so what I have done is I've taken equation A and I've replaced the y in equation B with the y value from up above. And so I've said sub A into B. And by doing that, what have I done? I've created an equation that has only one variable. So we can then proceed to rearrange and isolate. So we are going to clean up and get x is equal to -4. So that is telling me that the x value for our solution is going to be -4. So now I need to find its counterpart y. And as always, x equals -4 has to work in both equation A or B. So to find y, you're going to substitute x equals -4 into either A or equation B. So I'm going to put it in A. We will get y equals 2, replace the x with a -4, clean this up to get -8 plus 2 equals -6. So our solution then should be xy equals -4, -6. So let's just do a quick check. So if I replace x with -4, -4 times 2 is -8 plus 2 gives me -6. So it works in equation A. So I am doing a check, but I'm not doing a formal check. If I go into equation B and I replace x with -4, -4 subtract 1 gives me -5. So that leads me to believe that I've made a mistake. So I am going to go back and I can see where I went wrong. So here, when I brought this 2 over, it should have been -2, and instead I wrote -3. So in fact, my answer should have been -3. This is why you have to do your check in both equations. So I have to go back. It worked in the one equation, but not in the other. That's why the test is to do it in both. So I go back and I replace that with a -3. So that's going to give me a -6. And that will give me a -4. So then my answer is actually -3 and -4. So let's go back and check that. So if I replace x here with a -3 and I subtract 1, I do get -4. So I am checking, but I'm not writing out the process. And you want to do that check because you can catch your mistake. And it's important that you check it in both equations. Okay, let's go on to another example. Now this equation looks a little bit different because instead of it being in the form y equals, it's in the form x equals. That's a good indicator as well that the substitution method is a good option. When you have either x isolated or y isolated, then it's a good choice. So then 5y minus 1 is equal to x. So I am going to substitute A into B. So I'm going to replace this x here with 5y minus 1. Now this time our equation, when we do the substitution, we're left with an equation involving y. So we're going to isolate for y this time. So I'm rearranging. So 7y equals 14, so y is equal to 2. X will equal 5 times 2 minus 1, so 10 minus 1 is equal to 9. So our solution should be xy equals 9, 2, because we always start with the x. And then we can go through and do a quick check. If y is 2, 5 times 2 is 10, minus 1 gives me the 9. 13 minus 2 times 2 would be 13, take away 4 is equal to 9. So I'm feeling good about my solution. So we'll save the formal check till we get to the third example. Now this one is different from the previous two examples because in example number 1, each equation was in the form y equals, and in example 2, each equation was in the form x equals. In example 3, neither x nor y is isolated in either one of the equations. Now, when I look at the first equation A, one of the things I notice is that the numeric coefficient in front of the y is a 1. So that means that I could very easily take this equation and rearrange it to isolate y. So I can take this -3x and transpose it. And so now this is now a new variation of equation B. And I still have equation B, we redid equation A, and equation B is exactly the same. We're not changing it. So now when you look, this here, the 7 plus 3x, what is it equal to? It's equal to y. So what I'm going to do is I am going to replace the y in the second equation with 7 plus 3x. It's an equal expression for y in terms of x. So we are going to substitute sub A into B. So we're going to write 5x plus 2, but now the y value is 7 plus 3x. That's what we've done. We've replaced that y with an equivalent expression in terms of x. And now we have an equation involving one variable, just x, and we can clean this up and solve. So I'm going to apply the distributive law. So that'll be 14 plus 6x equals 3. Gather the x terms, transpose the 14. 11x equals -11, so x is equal to -1. So now I have to go back and find the y counterpart. So I can substitute that into either the original equation A, the new equation A, or into B. So I'm going to put it in this one here. Y equals 7 plus 3. Replace the x with -1. So that becomes 7 minus 3, so that is equal to 4. So our solution would be xy equals -1 and 4. Okay, and the reason I'm choosing this new variation of a is because y is already isolated. Now, in this case, I would go and do a formal check. So we're going to do a formal check in both. So we'll do a formal check. So for a, the left side is -x. I'm going to replace x with -1, and our y value is 4. So a negative times a negative is a positive. And when you add those together, you get 7. So the left side equals the right side. So we have verified that -1, 4 is a point on line A. Then we check it in line B. The left side is 5 times x, which is 5 times -1, plus 2 times y, which is 4. That becomes -5 plus 8, which is equal to +3. And our right side was +3. So left side equals right side. So we have verified that -1, 4 is indeed a point on line B. And because it is a point on line A and it's a point on line B, it must be the solution to our linear system. Okay. So the substitution method works when variables are isolated. So if x is isolated or y is isolated, then substitution is a good algebraic method to use for solving our linear system. So to recap, we have learned 3 different ways for solving linear systems using the graphical model and 2 different algebraic models, elimination and now substitution.